Hello students, welcome to my channel. Sorry for the poor quality of the third lecture on the de Broglie hypothesis. So because of that I am re-recording this lecture again for you, and let us hope this time the video quality disturbance is not there, and I am repeating the contents of the previous lecture again for you people. So let us now discuss formation of wave packet quantitatively. Now, in the lecture number 2 related with the de Broglie hypothesis, we conceptually understood that a wave packet is formed when a large number of de Broglie waves of different frequencies and wavelengths and traveling in different directions. Of course, they superimpose with each other. The desirable things is that all the waves which are combining to form the de Broglie wave packet must have different frequencies or wavelengths. So it means if I arrange all the waves of different wavelength in the wave packet in the increasing order of their wavelength or increasing order of their frequencies, then the difference in the consecutive frequencies or consecutive wavelengths of two de Broglie waves will be very small. So in that sense, if I consider two de Broglie waves, then I can write the shape of these de Broglie waves as follows. Let us say one of the de Broglie wave is given by the wave function psi1, and it is expressed as a sine omega t minus kx. Okay, the next wave function, the wave function of the next de Broglie wave, which is just adjacent to the one represented by equation 1, will be differing in frequency and wavelength from 1 just by small margin. So I can very easily write the form of the second wave function as sine a sine omega plus d omega into t minus k plus dk into x. Let us say this is equation number 2. So when these two waves will superimpose with each other, then the final displacement or final wave function after superposition will be given by psi is equal to psi 1 plus psi 2. So to write this, we will be adding psi 1 and psi 2. A will come common and it will become sine of, I would write here curly bracket, sine of omega plus d omega into t minus k plus dk into x plus sine of omega t minus kx. So this when added, if I assume that this angle is C and this angle is D, then we know that sine of C plus sine of D is equal to 2 sine C plus D by 2 and cos C minus D by 2. If I use this standard expression of trigonometry, then this equation would simplify as follows. Psi is equal to 2a sine omega plus d omega by 2 t minus k plus dk by 2 x multiplied by cos d omega by 2 t minus dk by 2 x. Let us say this is equation number 3. Now we can put 2a cos d omega by 2t minus dk by 2x equal to r. This is my assumption. I assume this quantity equal to a new quantity r, and since d omega and dk are small, therefore in the equation 3 I can neglect d omega by 2 when it is present along with omega. Similarly, I can neglect dk by 2 when it is present along with k, because it is negligibly small as compared to k. It is negligibly small as compared to omega. So I can neglect this d omega and dk term in the first part only. Here these cannot be neglected because these are not present along with omega and k. So if I use this approximation, then, and also if I use the value of this quantity equal to r, then equation 3 can be approximately written as psi approximately equal to it is approximately equal to r sine omega t minus kx. Now equation 5 is matching in form with equation number 1. Both of these equations represent a progressive wave having frequency omega and propagation constant k. However, what is the basic difference between both of these? That here the amplitude A is constant everywhere, and this was problematic for us because square of amplitude is the probability, and if amplitude is constant everywhere, then the probability of finding the object everywhere in the universe will be same, which is not possible for a physical object. On the other hand, if I look at r in equation 5, then r is the amplitude of this wave, and this wave is nothing, it is the equation of the wave packet that is obtained from the superposition of two waves. In the ideal wave packet, the number of waves will be infinite. The treatment I am using here is for engineering students. Actually, we must add all these infinite de Broglie waves to obtain the equation of a real wave packet or ideal wave packet. That is beyond the scope of my today's lecture. For that, I will advise the students who want to deal it with more depth. I will advise the students to refer to the book by Pawan and Graceman, according to me, which is the best book in this concept. We can see there that transforms, Laplace and Fourier transforms are quite useful there to obtain the actual form of the wave packet. Here I am not considering that, and that part is beyond the scope of my lecture. So this lecture is of more relevance to the engineering students rather than pure science students. Of course, pure science students can get the conclusions drawn from this lecture will be same as for the student as if we use Fourier transforms and Laplace transforms to obtain the actual equation of wave packet. So conceptually it can be useful for them also. Okay, now what is this r? If I look at equation number 4, r is a function of t as well as x. What is the meaning of this? The amplitude of the wave packet, which is represented by equation 5, the amplitude of this wave packet is a function of t at different values of x, and it is a function of x at different values of t. This is something which we require because a physical object must have different probabilities at different places at a given instant of time, and its probability should also be different at different times at a given place. So this is the direct meaning of this is that the amplitude must be a function of t and x, which is I am getting in equation number 4. So in that sense, r is a function of x and t, which is quite good for us. So now it means this equation represents a wave packet, and I have already discussed with you conceptually in the previous lecture that the velocity of the particle have chances of being equal to the velocity of the wave packet. Now there is a problem in front of us. How to find the velocity of wave packet? We know that the velocity of a single de Broglie wave is obtained by the ratio of omega to k. I have discussed that in my previous lecture. Now how to obtain the equation of a wave packet? For that, let us just get an idea for obtaining this answer. Okay, let us see. Now suppose this is minus infinity and this is plus infinity, and wave packet at a given instant of time is here and particle is somewhere in the wave packet. Kindly remember, the particle can never come out of this wave packet. If particle goes ahead, wave packet has to go ahead. If particle goes backward, the wave packet has to go backward. Why? Because the probability of finding the particle is proportional to square of the amplitude. Right now amplitude at this point and this point is 0. So therefore the particle's probability should also be 0 at all these points. However, the amplitude of the wave packet, although it is a variable, but in general it is not 0 within this envelope. So the particle is confined within this envelope. It cannot come out of this envelope. So therefore wherever the particle will go, the wave packet will also go there. Now this is very important for us. If we are capable of understanding or catching this point, this is an important observation, then we can very easily find the speed of the group or the wave packet. Now suppose at a later instant of time, the particle, let us say particle is progressing towards plus x axis, that at a later instant of time the particle reaches here. If the particle reaches here, then it is not possible that wave packet stays here. The wave packet must also reach here. So the shape of the wave packet at a later instant of time must be like this. So this envelope has now traveled at this place. Now it means we can find the speed of this wave packet just by finding the speed of any point in the wave packet of identical amplitude. Let us let us consider any point, maybe let us say this point. This point on the amplitude is here, although particle is here. Kindly remember, particle is here. I have chosen some point of some value of the amplitude. Let us say the value of amplitude when particle was here, the value of amplitude is here. So the same identical point when the, let us draw some different symbol, particle far shielded. Let us say this point is R dash. The same point R dash of identical amplitude reaches here. This point R dash reaches here. So therefore, if we want to find the speed of the wave packet, we can simply check the speed of this amplitude. If we see equation 4, amplitude R is oscillating. The equation 4 is matching again with the equation of a progressive wave. However, in this case, the quantity which is oscillating with respect to space and time is R. So this R, which is the amplitude of the wave packet, must be traveling with certain velocity. that velocity will be called as group velocity. So that group velocity Vg must be given by coefficient of T to the ratio of coefficient of x. Just as in this case we want to find the speed at which psi is traveling. Now psi is traveling with a speed which is called phase velocity. It is ratio of k, omega to k, and omega is nothing but coefficient of t, and k is nothing but it is coefficient of x. And now I am finding the speed at which r is traveling. So r is traveling with a speed which is equal to the coefficient of t, that is omega by 2, to the coefficient of x, that is dk by 2. It means this point r dash will go here from here to here with a speed vg. Now that vg will be equal to this ratio. Now I have already told you that coefficient of t is d omega by 2 to the coefficient of x is dk by 2. This 2 and this 2 will cancel. Vg is equal to d omega by dk. Let me call this as equation number 6. And this is the first expression for group velocity. It is the velocity of the wave packet attached with the de Broglie waves. Therefore, group velocity is the derivative of omega with respect to k. Now we can simplify this formula by just introducing Einstein-de Broglie relations. These relations are important for us. Therefore, I will introduce these two equations to you before using them in my equation number 6. We know that what are Einstein-de Broglie relations? We know that according to Planck's theory, E, energy of any wave packet, is equal to h nu. I can write this equation by h upon 2 pi multiplied by 2 pi nu. I have done nothing, just multiplied and divided this equation by 2 pi. Now this can be written as h cross omega, that is E is equal to h cross omega. This is equation number 7. Here h cross, or sometimes it is also written called pronunciated as h bar. It is 1.054 into 10 raised to power minus 34 joule into second is called Planck's reduced constant. Omega is of course the angular frequency. Similarly, according to de Broglie formula, which we already know, P is equal to h by lambda. I can write this equation as h upon 2 pi multiplied by 2 pi by lambda, and this is equal to h cross, and this is k, that is P is equal to h cross k. Now equations 7 and 8 combinedly are called Einstein-de Broglie relations. I can use both of these equations to just get another form of equation number 6. How? Let us see. Vg, which is equal to d omega by dk, can also be written as h cross upon h cross d omega by dk. Here I have divided and multiplied by h cross on the right hand side. Since h cross is a constant quantity, I can take it inside the differentiation. So it will become d of h cross omega to d of h cross k. So by using Einstein-de Broglie relations, h cross omega is nothing but the total energy of the wave packet, and h cross k is nothing but the linear momentum of the wave packet. Here I am using the term wave packet. You can easily use the term energy of the particle or wave momentum of the particle, because whatever energy and momentum the wave packet is possessing, it is due to the particle. The energy and the momentum of the wave packet is always equal to the energy and momentum of the particle. So I can write Vg equal to dE upon dP. So we have now two expressions for group velocity. The first expression is given by equation number 6, according to which it is the derivative of omega with respect to k, and according to 9 it is the derivative of E, total energy, with respect to magnitude of the linear moment. Now we want to check whether this group velocity is equal to particle velocity or not. To do that, we have to use results of special theory of relativity. The first result of special theory of relativity we must remember is that E is equal to mc square. This is the first equation that we must remember. It is called Einstein's mass energy relation. It is quite a famous relation. I guess everybody amongst you must have the knowledge of this equation. If you don't have, then kindly remember it for the time being, because theory of relativity is not my topic of teaching right now. I will be giving lectures on the special theory of relativity, of course, but at a later stage of time. Till then, you remember this result. Similarly, the total energy according to Einstein theory is also given by E is equal to square root of m naught square c4 plus p square and c square. This equation is called energy momentum relation. And here P is the magnitude of linear momentum, m0 is the rest mass of the object under study, and C is the speed of light in vacuum. E is of course the total energy of the particle. I have to use both of these equations. Now if I let us say this is equation number 10 and this is equation number 11. If I square equation number 11, I would get E square is equal to m naught square c4 plus p square c square. Take the derivative of this equation with respect to p on both sides, then we will get 2e dE by dt. This quantity is constant, so its derivative will be 0, and c square is constant, it will come outside, and derivative of p square will be nothing but 2p. Therefore, I can write dE by dP is equal to c square into 2p upon 2e. 2 and 2 will get cancelled. Now what is p? That is the linear momentum of the object. It is always equal to mass in the motion, mass in motion, and velocity of object. Velocity of object is of course written by symbol v, and E is given by equation 10 also. It is m and c square. Now m cancels with m, c square cancels with c, and dE upon dP is nothing but Vg. Hence, I get the result Vg is equal to V. This is equation number 12. So therefore, I have proved that actually group velocity is equal to particle velocity. This is something we expected when we discussed these things conceptually in lecture number 2 of the de Broglie hypothesis topic, and today we have proved it quantitatively by using mathematics and results of special theory of relativity. So therefore it is indeed true that particle is traveling with the speed of the wave packet rather than speed of a single de Broglie wave. And the speed of the wave packet is obtained by finding out the average of the all de Broglie waves that are constituting the wave packet. Now, however, it remains to prove that Vg can be less than C. Although we discussed it conceptually in the previous lecture that it is possible if the waves forming the wave packet, they superimpose with each other in out of phase manner. Out of phase does not mean actually 180 degree. Out of phase means the phase difference between them should not be 0 degree. Right now here I mean it by this. So different waves which are superimposing with each other to form the wave packet must have different phase, must have different frequency, must have different wavelength, and may or may not have same amplitude. Their amplitudes can also be different, and we just have to find the condition under which Vg can be less than C. If I am able to find that condition, and if we are able to find that condition and we are able to satisfy ourselves that that condition can be really met, then obviously it is it is a correct direction in which our theoretical model is moving, and then the equations will just be need to be validated by using an experiment. And that experiment, I have already told about that experiment. Its name is Davison and Germer experiment, that we will discuss in the later lecture. But today we will be developing mathematical model and trying to just prove that Vg can be less than C under certain circumstances, and let us find that circumstances. Okay, to find that we have to now, that condition is called dispersion relation. Dispersion relation for de Broglie waves. It's not the new article, it is the same article. Under I have just given it a heading just to tell you that it is something which is related with the dispersion. Now let to go for this topic, instead of going to this topic straight away. Let me just recapitulate the dispersion that we have studied in case of light. What was the dispersion in case of light? If this is a prism, you can skip this portion of the lecture if you have the knowledge of dispersion, but those who do not have the knowledge of dispersion, they may find this part, these 4 or 5 minutes, to be interesting. Otherwise it's not this portion, dispersion of white light, is not a part of this article, of course, and it is just for recapitulation. Suppose white light enters on the prism, then this white light bends and spreads into several colors. These colors were called as Vibgyor, Vibgyor. And the maximum color that will bend will be violet, and the minimum color that will bend will be red. So now this is called dispersion. When white light passes through a prism, it splits into 7 colors, or instead of 7 colors I can use the term its component colors, whatever, because white light is actually made by these component wavelengths, and when white light passes through prism, it splits up into component colors. So this is called dispersion. If I want to find the angle of deviation, then this is the incident ray, this is the angle of deviation for red color, and this is the angle of deviation for violet color. And we see that the maximum deviation is suffered by the ray having violet region, and the minimum deviation is suffered by the ray in the red region. Now the why this happens, this explanation was given by Cauchy. According to Cauchy, the refractive index mu of a medium is a function of the wavelength of the incident light according to this expression. Actually this is an endless series. However, if C1 and C2 are called Cauchy's coefficients, however, if we neglect the higher terms, we can approximate this result up to second coefficient, because the value of Cauchy's coefficients these go on decreasing for higher order terms. So just I would restrict up to second term. If this is true, then what we can see that if lambda is high, then according to this equation mu will be less. Now we also know that speed of light in medium is given by c divided by v, c divided by mu. Now if I just remember this equation, speed of light in a medium is equal to c by mu, then since mu is in the denominator and mu has decreased, this will mean that speed will increase. So what is the effect of dispersion on the speed of light? Higher wavelengths in a medium will have higher speeds. It means since higher wavelength is of red color and lower wavelength is of violet color, in vacuum all colors lights travel with the same speed, that is speed of light, that is 3 into 10 raised to the power 8 meter per second. However, as soon as this white light enters in any medium, then the speed of light in the red region will increase as compared to the speed of light in the violet region. Also, if this is angle of prism, it is also called refracting angle, then angle of deviation delta is given by mu minus 1 into A. If again I use this expression that high lambda means low mu, and low mu according to this expression will give me low delta, and this will very easily explain me why red color has bent less and why violet color has bent more. So according to this formula we must conclude that higher wavelengths bend less and vice versa. So any relation which relates the refractive index with respect to wavelength, or speed with respect to wavelength, or angle of deviation with respect to wavelength is called a dispersion relation. Why? Because it will explain that different wavelengths of different waves of different wavelengths will have different speeds with different deviations and different refractive indices. So a dispersion relation is in general any relation between the wavelength and other parameters of the light like speed and refractive index of a medium, etc., and angle of deviation. Let us now, this part you can probably skip from my lecture if you have already the knowledge about this topic. Let us now go to the dispersion relation in de Broglie waves. Now, how to obtain the dispersion relation between de Broglie waves? We know that the phase velocity of de Broglie waves is the ratio of omega to k. Therefore, I can write omega is equal to k and Vp, and the group velocity, which is equal to d omega upon dk, can be written as d upon dk of kvp. I will apply product rule here. If I apply product rule here, then this equation will become Vg is equal to Vp plus k dVp by dk. I can just simplify it further by writing it dVp plus k into dVp, Vp plus k into dVp by d lambda into d lambda by dk. Now we know that k is equal to 2 pi by lambda. Therefore dk by d lambda is nothing but minus 2 pi upon lambda square. If I put this value here, then I will get Vg is equal to Vp minus plus 2 pi by lambda into dVp by d lambda into minus lambda square upon 2 pi. Now this 2 pi will cancel with 2 pi, lambda will cancel with lambda, this minus will come ahead, and Vg will be equal to Vp minus lambda d Vp upon d lambda. I would just call this as equation number 13. Equation number 13 is called dispersion relation. Here I think I forgot to write subscript P. So Now this equation is called dispersion relation. Let us see what are the possibilities that we can get from this dispersion relation. First case we can have is that, for example, let us say case 1. Suppose the value of Vp is independent of lambda. So I have already discussed with you that in case of dispersion, speed becomes a function of wavelength. Now what is the case 1 describing? It is saying that velocity Vp is independent of lambda. It means all de Broglie waves of different wavelength will travel with the same speed. Means I am discussing the case of no dispersion at all. Means de Broglie, it's just my assumption that de Broglie waves are not showing any kind of dispersion. If it happens, then what equation 13 will give to us? So since Vp is assumed to be independent of lambda, therefore dVp by d lambda will be 0. And if I put this in equation number 13, then I will get Vg is equal to Vp. Now this is strange and unacceptable. Cross means unacceptable. Why? Because we know that Vp being equal to c square by V is always greater than c, and Vg equal to V. I have just proved it. And V is the speed of an object which is always less than c. So a quantity in left hand side of this equation is less than c, and right hand side of this equation is greater than c, and therefore you cannot have equality between them. So therefore I will reject this case. It means case 1, which says that Vp is independent of lambda, is not ideal for our situation. If de Broglie waves are in fact reality, these are attached with a particle, then these must show dispersion. The case of no dispersion is not acceptable to us. De Broglie waves of different wavelengths must travel with different speed. Let us now discuss case 2. De Broglie waves must show dispersion. This is something which we get till point. What kind of dispersion? We want to check it out. Let us say case 2. Suppose dVp by d lambda is negative. Now, we know that if the derivative of a quantity is negative, that quantity is called decreasing. Since here dVp by d lambda is negative, it means Vp is a decreasing function of lambda. It means higher wavelengths will mean low speed. Now this is not something which we discussed earlier in my 5 minutes discussion in the same lecture for light. In case of light, higher wavelengths have high speed and lower wavelengths have low speed. And in case 2, we are just seeing that if dVp by d lambda is negative, then higher wavelengths will have low speed and vice versa. So therefore this kind of dispersion is unlike light. It's not like light. It is unlike light. It is called anomalous dispersion. Anomalous dispersion. Now if de Broglie waves show anomalous dispersion, what would we get from 13? So from 13 we see that since dVp by d lambda is negative, therefore Vg will be equal to Vp plus something positive. Why? This negative and dVp by d lambda is also negative, so negative into negative positive. So therefore Vg will be equal to Vp plus something positive. So Vg will be greater than Vp. However, we also know that Vp is greater than C. Now Vg is greater than Vp and Vp is greater than C. If I combine both of these conditions, this will mean Vg is greater than C. Now this is again unacceptable. Why? Because Vg is equal to V, and V, which is the speed of object, is always less than C. So this kind of dispersion is not serving my purpose. Therefore, from case 1, we just concluded that de Broglie waves must show dispersion. From case 2, we concluded that the dispersion shown by de Broglie waves can not be anomalous dispersion. Now we have just third case remaining. If that case serves our purpose, then it's well and good. Our model is moving in the correct direction. Otherwise, it will be a trouble for us to develop a theoretical model for de Broglie waves attached with the matter. Now, what is the case 3? Case 3 says that let dVp by d lambda is positive. If dp by d lambda is positive, it means Vp is an increasing function of the wavelength. What is the meaning of this? If higher is lambda, that would mean Vp will also be higher. This is something which is same as shown by light waves. In case of light waves, when light waves enter in any medium, then higher wavelengths travel with high speed and vice versa. This is same. So de Broglie waves in case 3 will show similar dispersion as is shown by light waves. So it is called normal dispersion. So case 3 is called normal dispersion. So what will be obtained? What information can we extract from case 3? Now what was Vg? I incidentally erased that equation. Vg was given by Vp minus lambda dVp by d lambda. Now this quantity is positive and this minus sign, positive into negative, will make it negative. Therefore Vg will be equal to Vp minus something positive. Now something is being subtracted from Vp. It means definitely Vg will be less than Vp. Now this is something which is a good news for us, because if Vg is less than Vp, then it can happen that Vg is less than C also. We actually need Vg less than C. Here we are getting Vg less than Vp. We are not getting Vg less than C. So, but however, if Vg is less than Vp, then there should be some extra condition that Vg can be less than C. But one condition is good for us, that if de Broglie waves are attached with the particle, then these de Broglie waves must show normal dispersion. These must show normal dispersion. Only then Vg has a possibility of becoming C. Let us see that possibility occurs under what condition. Now we want Vg less than C. If I put the value of Vg, this means I need Vp minus lambda dVp by d lambda less than C. I can take this quantity on the right hand side. So that will give me Vp minus C less than lambda dVp by d lambda, or lambda dVp by d lambda is greater than Vp minus C, or lambda or dVp by d lambda must be greater than Vp minus C by lambda. Now this equation, this was I think equation number 14 13 I have already taken that number. This must be equation number. It's not equation, it's a condition rather. So this condition tells me that if de Broglie waves show normal dispersion, first thing dVp must be positive, dVp by d lambda must be positive, and the rate of change of Vp with respect to lambda must be greater than this quantity, then Vg will be definitely less than C. Therefore, this condition has to be satisfied for the velocity of the group waves to be smaller than the velocity of the light. So, this is the essential condition. Since therefore we have just seen that our theoretical model can have the validity if this condition is satisfied. Since the experimental proof of wave nature of the matter has already been obtained through Davison and Germer experiment, where it was proved by these two scientists that electron beam from bismuth actually showed diffraction, and diffraction is a property of waves only. So therefore the wave nature of electrons is proved. Since electron is the smallest material particle, independent material particle, because we have this particle smaller than electrons also, but the electron beam has been produced by cathode rays. We know that we can simply produce electron beam, independent electron beam, and if the diffraction of electrons has been observed, and all matter contains electrons, therefore every matter must show diffraction. So therefore the wave nature of the matter has been already proved by the Davison and Germer experiment, which indicates that this condition 14 in fact exists and has been validated in the universe by the nature. So today's lecture ends up here, and in this lecture we were able to develop a mathematical model and to just validate our discussion of the lecture number 2, where we just apprehended what should be the nature of the de Broglie waves and under what conditions we can have formation of the wave packet. And I would just summarize that the wave packet is formed by the superposition of infinite number of de Broglie waves, and the discussion carried out by me in this lecture was not for the infinite de Broglie waves. It was in that part my lecture is just subdued from the actual treatment, and these waves must show the normal dispersion, and the rate of change of velocity of de Broglie waves with respect to lambda must be greater than this quantity, this value. Hopefully now I assume that you have just enjoyed today's lecture, and you will be benefiting from this lecture, and we will discuss more about de Broglie's nature, de Broglie's hypothesis in my next lecture. I am going to replace the previous lecture number 3 with this lecture. Till then, goodbye, and hopefully we will meet for the 4th lecture again. Thank you very much.